if you've been paying particularly close attention to our use of the factorial operator and in the videos on permutations and combinations, you may or may not have noticed something that might be interesting. So let's just review factorial a little bit. So if I were to say n factorial, that of course is going to be n times n minus, times n minus 1 times n minus 2, and I would just keep going down until I go to times 1. So I would keep decrementing n until I get to 1, and then I would multiply all of those things together. So for example, and all of this is review, if I were to say 3 factorial, that's going to be 3 times 2 times 1. If I were to say 2 factorial, that's going to be 2 times 1. 1 factorial, by that logic, well, I just keep decrementing until I get to 1, but I don't even have to decrement here. I'm already at 1, so I just multiply it 1. Now, what about 0 factorial? This is interesting. 0 factorial. So one logical thing to say, well, hey, maybe 0 factorial is 0. It's, I'm just starting with itself. It's already below 1. Maybe it is 0. Now, what we will see is that this is not the case. That mathematicians have decided. And remember, this is what's interesting. The factorial operation, this is something that humans have invented, that they think is just an interesting thing. It's a useful notation. So they can define what it does. And mathematicians have found it far more useful to define 0 factorial as something else. To define 0 factorial as, and there's a little bit of a drum roll here, they believe 0 factorial should be 1. And I know, based on the reasoning, the conceptual reasoning of this doesn't make any sense. But since we've already been exposed a little bit to permutations, I'll show you why this is a useful concept, especially in the world of permutations and combinations, which is, frankly, where factorial shows up the most. I would say the most of the cases that I've ever seen factorial in anything has been in the situations of permutations and combinations, and in a few other things, but mainly permutations and combinations. So let's review a little bit. We've said that, hey, if we have n things and we want to figure out the number of ways to permute them into k spaces, it's going to be n factorial over n minus k factorial. Now we've also said that if we had n things that we want to permute into n places, well, this really should just be n factorial. The first place has, let's just do this. So this is the first place, this is the second place, this is the third place, all the way you get to the nth place. Well, there would be n possibilities for who's in the first position, or which object is in the first position. And then for each of those possibilities, there would be n minus 1 possibilities for which object you choose to put in the second position, because you've already put 1 into that position. Now, for each of these n times n minus 1 possibilities where you've placed 2 things, there would be n minus 2 possibilities of what goes in the third position, and then you would just go all the way down to 1. And this thing right over here is exactly what we wrote over here. This is equal to n factorial. But if we directly applied this formula, this would need to be n factorial over n minus n factorial. And then you might see why this is interesting, because this is going to be n factorial over 0 factorial. So in order for this formula to apply for even in the case where k is equal to n, which is this one right over here, and for that to be consistent with just plain old logic, 0 factorial needs to be equal to 1. And so the mathematics community has decided, hey, this thing we've constructed called factorial, we've said, hey, you put an exclamation mark behind something in all of our heads. We say you kind of count down that number all the way to 1 and you keep multiplying them. For 0, we're just going to define this. We're just going to make a mathematical definition. We're just going to say 0 factorial is equal to 1. And it's actually quite useful.